Okay, so this is Giancoli, Chapter 16, Problem 31, and we are asked to determine the direction and magnitude of the electric field at point P in the figure given. And what's going on here is you've got one charge of plus Q, another charge of minus Q, and I'm going to mark this place here. We're interested in what's going on at point P, which is here, along the same line with these other two charges. And the distance from this center point to this charge here is A, and this distance is also A. And we are supposed to figure out, given their separation, what is the direction and magnitude of the electric field. And we're going to express our answers in terms of Q and X, A, and K, and we want to boil this down to one term. So, okay, first of all, we're asked to figure out what is the electric field. And what we have here are 2-point charges, so we want to think about how do we figure that out for this combination of things. Recall the electric field, that is, it's defined in terms of the force, the electric force acting on a particular test charge, little q, but then you divide that by that charge of that test charge, Q, and it tells you about the nature of this thing we call the electric field everywhere. Can be, in principle, calculated if you know the force and you know the charge on a test. Now, it turns out for a single point charge, so point charge, the magnitude of the electric field produced by a point charge is given by K Q over R squared. Q is the charge in question, and R is the distance from that point charge. Now that's the magnitude, and then of course the direction, you figure that out based on the sign of the charge Q. So technically I should put an absolute value around there. So what we need to do then is figure out what is the electric field at this point due to this positive charge, and what is it due to the negative charge, incorporating the signs in there. So let's go ahead and do that. The total electric field, which I will now indicate the direction, the electric field due to this positive charge. So we're going to write down K, we're going to write down its charge, it's Q, and we'll write down, well, it gets divided by the distance squared. From P to this center point, that's a distance x, and now it's a little bit further than that. It's actually x plus a, so that's what goes down here. It's x plus a, and it gets squared, and we know that at this point, the field should be pointing to the right. If you like, the field should be pointing away from the positive charge. So I will I'm going to explicitly write a plus sign there to let us know, yes, it should be pointing to the right. Now, let's add to this. The way that electric field, the total electric field is found is by adding up the electric field due to every point charge that you have. We have this negatively charged thing, so K, its charge, negative Q, and divide by the distance to it. Well, it's x less the distance a, so it's x minus a squared. And does it point in the right direction? Well, with this negative sign, that means this contribution points in the other direction, to the left, as it should, because this is a negatively charged charge. So here we go. We have things set up correctly. This is pointing to the right. This is pointing to the left. Let's now combine, or let's see, factor out the common factor of K and Q, and that apparently gets multiplied by 1 over x plus a squared, and there's a minus sign, x minus a squared. And now we technically have everything we need, but I want us to simplify this into one term. So we have the difference between two fractions with different denominators. We should find a common denominator, and perhaps the most straightforward way to do that is to multiply the top and bottom of this fraction such that it'll pick up a term that looks like this bottom, and we'll do the same thing over here. So in fact, let's do that, KQ. On the top then we'll have an x minus a squared, so that on the bottom we have x plus a squared times x minus a squared. In other words, we've just multiplied by 1. And we'll do the same thing over here. On the top and the bottom we'll multiply by x plus a squared, and on the bottom we will have the same thing. Okay. And now that we've done that, we can bring this all together, this is apparently KQ times the quantity of x minus a squared minus x plus a squared, and all that's divided by this. And in fact, there's a simple way to write this. Remember, x plus a times x minus a is x squared minus a squared, and you do that twice. So in fact, this is x squared minus a squared quantity squared. And in the brackets here, what we should have is KQ. And let's work this all out. X minus a quantity squared, that's x squared minus 2 times the cross plus a squared. And then subtract off everything that you get from squaring this term. In other words, x squared plus 2xa plus a squared. And the bottom is all, I'll just write same. It has not changed from the line above. The x squared and the x squared cancel. The minus 2xa and another minus 2xa, that stays around. A squared minus a squared, those cancel. So in the end, you have, I'll put this up here, it appears that the electric field has an overall minus sign. Let's pull that out. A 2 and a 2 makes a 4. And I'll keep the k and the q and the x and the a, and this gets divided by x squared minus a squared quantity squared. And now the fact that there's an overall minus sign tells us that the thing should be pointing to the left. Does that make sense? Well, we know that the positive charge makes a field that points to the right, negative charge to the left. But because we are closer to the negative charge, that should dominate the orientation of the field. So this negative sign is correct. So if you like, you can write it like this or indicate that the electric field value is this thing without the minus sign pointing to the left, however you want to do it. The last thing I'm going to point out is that notice that as x becomes very, very big compared to a, you might ask, what does the field look like? What does the electric field look like due to this dipole? Well, in that limit, you can neglect the a squared relative to the x squared when you're adding or subtracting these things. So what that means is on the bottom, the electric field behaves like asymptotically as minus 4 k q x a over x squared squared, in other words, x to the 4th, which means that this is approximately equal to minus 4 k q a over x cubed. Okay, so what that means is that the electric field due to a dipole behaves like 1 over the distance cubed rather than 1 over the distance squared.